Alright, now let's move on to the next agenda, big data. The term big data implies not only the big volume of data. IBM's definition is widely used to conceptualize big data, 3 V's, 4 V's, or 5 V's. Some articles introduce only the first 3 V's, volume, velocity, and variety. Others introduce the fourth one, veracity, and sometimes the fifth one, value as well. But the first 3 V's are the key to characterizing big data. First, volume. Big data definitely indicates larger amounts of data generated from a range of sources, but not only the volume, but also the others. Second, variety. In big data, there are multiple kinds of data that involve a situation or event to be investigated. For example, social media generates structured user log data plus unstructured text, pictures, audio, and video data. Third, velocity. A tons of data is generated a day, an hour, a minute, and a second, and the data generation is getting faster and faster and faster. In line with the data generation, we also need to speed up decision making. For example, YouTube's recommendation system works in real time to reflect so many video clips newly generated every second. To handle big data in real time, computing speed is also very important. Computer scientists developed solutions based on MapReduce concept. Suppose that there is a computational task with big data and let's call the task an application. MapReduce breaks the application into several sub-problems. First, MapReduce is doing map, which means assigning the sub-problems to nodes of computers. Then it is doing reduce, which means combining the results from the sub-problems. This MapReduce concept allows for distributed or parallel computing to handle 3 V's of big data. Most popular solution is Hadoop, which is an open source version of MapReduce. So, big data allow us to access a large number of data from new perspective in real time. Then, how to extract valuable information from big data? Google Flu Trends might be the first famous attempt. People ask Google when they need information, especially when being sick. So many people ask Google first instead of visiting doctors because my doctor is so far from me, but Google is always next to me. Flu is one of that kind of sickness, so Google brought up a hypothesis. If an influenza epidemic is coming, an increasing number of people may show health-seeking behavior in the form of queries to online search engines. So, Google collected weekly counts for Google search queries over 5 years from 2003 to 2008 and developed a model to track influenza-like illness, ILI in short, in a population. This figure displays the fitting and prediction performance. Black curve is Google's estimate of ILI percentage for the Mid-Atlantic region, and red curve is CDC reported ILI percentage. We can find that the performance is pretty good enough to use in reality. Especially, the prediction performance was amazing. Correlation between the predicted and CDC reported values was 0.96. However, Google Flu Trends finally failed. This science article explains the failure of Google Flu Trends. The authors introduced big data hubris. That is, people often assume that big data are a substitute for, rather than a supplement to, traditional data collection and analysis. That is, the foundational issues of measurement, validity, reliability, and dependencies among data are still alive in analysis with big data. From the late of 2011, a systematic discrepancy between predictions and CDC reported values appeared. Combining Google Flu trends with other traditional data, like lagged CDC data, significantly reduces the discrepancy. Why this happened? The authors introduced the concept of algorithm dynamics. Algorithm dynamics are the changes made by engineers to improve the commercial service and by consumers in using the service. Several changes in Google search algorithm and user behavior likely affected GFT, the Google Flu Trend Tracking. The Google search algorithm is not a static entity. The company is consistently testing and improving search, and the changes affected search behaviors. For example, Google reported in June 2011 that it had modified its search results to provide suggested additional search terms and reported again in February 2012 that it was now returning potential diagnosis for searches including physical symptoms like fever and cough. The former recommends searching for treatment of the flu in response to general flu inquiries, but the latter explains the increase in some searches to distinguish the flu from the common cold. Here I want to quote the key point of the article. GFT bakes in an assumption that relative search volume for certain terms is statically related to external events, but search behavior is not just exogenously determined. It is also endogenously cultivated by the service provider. This is what Google Flu Trend missed. This example implies that big data is a really good, game-changing weapon, but it does not change the rule of war. Now, I'm going to briefly talk about the third topic, artificial intelligence. As well as AI and machine learning, you may hear deep learning from lots of people and media. What is the difference among them? AI is a conceptual term. It includes any effort to automate intellectual tasks which are normally performed by humans. An example is interactive voice response. When you call a company, now a machine with human voice is welcoming you. It guides you to the service that you may need or the best representative person who can solve your problem. Of course, it is not perfect. Sometimes I just want to directly talk with the representative person, but anyway, it is the most popular AI in real life. Machine learning is a part of AI. It is an algorithm or a set of algorithms to search for useful representations and rules of data. We already discussed what machine learning is in details in the first part of this lecture. Deep learning is a way of machine learning. It has multiple layers to learn data representations, and the number of layers can be very large. That's why it is called deep learning. It has received attention because it allows for automating many tasks that we've failed to automate. This is a short list of what we can do with deep learning now. AIs with deep learning now easily beat human at professional board games like Go and chess. And in many tasks, including image classification, speech transcription, handwriting transcription, autonomous driving, AIs show near human level performance. Those developments now allow for natural language process like translation, text-to-speech conversion, and answering natural language questions. Those lead to release of digital assistants such as Google Now and Amazon Alexa. In marketing, AI technology based on deep learning algorithms has widely used for ad targeting and recommendation system. Alright, that's all I have in this lecture. In the exercise after this lecture, you will learn dynamic factor analysis, which is an unsupervised learning method for characterizing search trend data. The exercise is based on this article, Quantitative Trend Spotting, by Rex Du and Wagner Kamakura. The article is available in Carmen. And thank you.